In 1965, Richard Feynman walked up to a stage in Stockholm to receive the Nobel Prize in physics. He had spent nearly 2 decades on the work being honoured. He had reshaped how physicists thought about light, electrons, and the strange interactions between them. And yet, when he later wrote about the very calculation that earned him that prize, he chose a peculiar word for it. He called it Hocus Pocus. That is not the kind of thing you expect from a man being celebrated as one of the greatest scientific minds of the 20th century. Feynman was not being modest, and he was not joking. He genuinely believed that the trick at the centre of quantum electrodynamics, the technique known as renormalization, was a kind of mathematical sleight of hand. A dippy process, in his exact words. A shell game that somehow gave the right answers but should not have worked at all. So here is the puzzle that drives this video. If the man who won the Nobel Prize for the theory thought the central trick behind it was nonsense, why is renormalization not only still in use today, but considered by many physicists the single most important advance in theoretical physics over the last 50 years? Why did something that looked like cheating turn out to be one of the deepest insights into how reality is structured? And what changed between Feynman's suspicion in 1965 and our current understanding? If you stay with me, you will not just learn what renormalization is, you will learn why every modern theory of fundamental physics, from the Standard Model to condensed matter to cosmology, owes its working life to a procedure that once looked like fraud. Let us start with the problem that nearly killed quantum field theory before it ever got off the ground. In the 1930s, physicists were trying to describe the electron, not just as a particle, but as something that interacted with the electromagnetic field around it. The mathematics of this interaction is the heart of quantum electrodynamics, or QED. And on paper, the theory was beautiful. It treated the electron and the photon, the particle of light, as ripples in deep underlying fields. It was elegant. It was unifying. There was just one small problem. When you actually tried to calculate something with it, the answers came back as infinity. Not occasionally, not in some exotic edge case, in ordinary calculations. The mass of the electron, the charge of the electron, the energy of the simplest interactions. Push the math too far in any direction, and the equations refused to give you a number. They handed you a divergent integral that ran off to infinity and stayed there. For a theoretical physicist, this is a special kind of nightmare. It is one thing to have a theory that disagrees with experiment. You can fix that. It is another thing entirely to have a theory that does not produce numbers at all. By the late 1930s, some of the smartest people in the world were quietly worried that field theory was a dead end, that the whole approach to particle physics needed to be torn down and rebuilt from scratch. Then the war came, and physicists scattered into other projects. When they returned in the late 1940s, 3 of them, working largely independently, found a way around the wall. In Japan, Shinichiro Tomonaga had been building a relativistic version of quantum electrodynamics in near isolation. In the United States, Julian Schwinger was developing his own dauntingly formal mathematical framework. And then there was Feynman, who took an entirely different route. He drew pictures. The diagrams that now bear his name reduced the most complicated interaction calculations into little stick figure cartoons of particles meeting and exchanging photons. It was visual, it was intuitive, and most importantly, it worked. But all 3 men, despite their different methods, ran into the same infinities. And all 3 had to do the same uncomfortable thing to get rid of them. They had to renormalize. Now here is what renormalization actually does, in plain terms. When you set up a calculation in QED, you are summing over an enormous number of possible quantum interactions. Most of these involve very high energies and very small distances near the electron. When you try to add them all up, the contribution from those very high energies and very short distances explodes. That is where the infinity comes from. The renormalization trick goes like this. You cut the sum off at some point. You say, I will not include contributions above this energy or below this distance. With that cutoff in place, the answer is finite. Then you take that finite, made-up answer and you do something strange. You absorb the part that wanted to become infinite into the value of the electron's mass and charge. You replace those theoretical values with the actual measured values from the laboratory. And finally, you let the cutoff go away again. The infinities cancel out. What remains is a beautifully precise prediction. That prediction is so precise that QED ended up being the most accurately tested theory in the history of science, agreeing with experiment to roughly 1 part in a billion. But you can see why Feynman called it Hocus Pocus. To his eyes, this looked like sweeping the dirt under the rug. You had a theory that produced infinities. You defined those infinities away by saying you would just use experimental numbers wherever they appeared. And somehow it all worked. It was a recipe, not an explanation. Feynman, Schwinger and Tomonaga were given the 1965 Nobel Prize for it. And in his Nobel lecture, Feynman essentially told the audience that he still did not really understand why his own technique was allowed. Paul Dirac, one of the founders of quantum mechanics, was even harsher. He called it not sensible mathematics. He could not accept that a respectable theory would tolerate such a procedure. This is where the story becomes genuinely beautiful, because the answer to why renormalization works did not come from particle physics at all. It came from magnets. In the 1960s, a physicist named Leo Kadanoff was studying the behaviour of magnetic materials near a critical temperature. As you heat certain materials past a specific point, they suddenly lose their magnetism. The patterns of how this happens turned out to be governed by a strange kind of self-similarity. The arrangement of atoms looked the same whether you zoomed in or zoomed out. Kadanoff developed a method called block spinning, where you average over groups of atoms to see how the larger scale behaviour arises from the smaller scale interactions. Then came Kenneth Wilson. Wilson was a former student of Murray Gell-Mann, and he had his feet planted in 2 worlds at once. He understood the formal machinery of quantum field theory, and he understood the messy, scale-dependent world of condensed matter physics. He took Kadanoff's ideas, combined them with earlier work by Gell-Mann and Francis Lowe, and produced something now known as the renormalization group. Wilson's insight was this: renormalization is not a trick to hide infinities. It is a description of how the laws of physics change when you change the scale at which you look at them. Different scales reveal different effective theories. The infinities that worried Feynman were not bugs. They were a signal. They were telling physicists that they were trying to push their equations down to distances where the theory was no longer supposed to apply. Think of it like this. If you study a fluid by looking at a single water molecule, you do not see waves. You do not see whirlpools. You do not even see liquidity in any familiar sense. Those phenomena emerge only at larger scales. The smooth equations we use to describe water flow are an effective theory of what happens when you zoom out far enough that individual molecules blur into a continuous medium. Quantum field theory, Wilson realised, is the same kind of thing. QED is not a description of the universe at every possible scale. It is an effective theory that works extraordinarily well within a specific range of distances and energies. The cutoff that Feynman, Schwinger and Tomonaga used was not a mathematical fudge. It was an honest acknowledgement that their theory had a domain of validity, and beyond it, new physics could, and probably did, appear. Wilson published this picture in 1971. He won the Nobel Prize for it in 1982. And from that moment on, renormalization stopped being a guilty secret and became one of the central organising ideas in all of physics. Today, the renormalization group is everywhere. It explains why phase transitions in completely different materials follow nearly identical mathematical patterns. It is the reason the standard model of particle physics, which describes every fundamental force except gravity, gives sensible predictions at the energies of the Large Hadron Collider. It is essential to our understanding of quantum chromodynamics, the theory of the strong nuclear force. It even shapes how cosmologists think about the early universe, where energy scales we cannot reach in any laboratory once dominated. The Cambridge theorist David Tong has called renormalization arguably the single most important advance in theoretical physics in the past 50 years. That is a strong claim. But once you understand what renormalization is really doing, the claim is hard to argue with. So why did Feynman, who helped invent it, never come around? Part of it was temperament. Feynman trusted experiment above all things, and he did not like writing checks his mathematics could not cash. Even after Wilson's work, he remained suspicious that the techniques were getting more credit than they deserved. He was a man who valued rigour as much as results. But there is also something deeper here, and it is worth sitting with. The story of renormalization is the story of a procedure that worked long before anyone understood why it worked. The men who built it knew it gave the right answers. They did not know what those answers meant about the structure of the universe. It took an outsider, Wilson, with 1 foot in particle physics and 1 foot in condensed matter, to recognise that the trick was actually a window into a deeper truth. That nature is organised into scales, and that the physics of one scale does not necessarily reach into the physics of another. That is a humbling lesson for anyone who studies fundamental science. Sometimes the strangest thing in a theory is not its weakness. It is its unfinished message. Sometimes Hocus Pocus is just understanding waiting to be born. If you found this useful, you can support the channel by liking the video and subscribing. There is more to come on Feynman, on quantum field theory, and on the strange, beautiful machinery that makes our best physical theories work. Thank you for watching. I will see you in the next one.